CLI and a cross-platform IDE for C and C++. Download now.
Welcome to my talk. I'm going to talk about continuous integration for large-scale C++ projects. This talk is the result of years of feedback from users. Some of you are here in the room, so thanks for it, because it has really a lot of feedback from many users to come up to this point. My name is Diego. I am one of the Conan co-founders, and I'm also leading the Conan project within JFrog. So I've been working for JFrog for 8 years, leading the whole Conan team there. Okay, so when we come to an organization or to a C++ project, we have to make a decision. And the first decision that we have to make is the development paradigm that we want to use at that organization. I'm talking for relatively large-scale C++ projects. And this is the decision that we have to make. We have to decide between a component-based paradigm and mono-repo-based paradigm. And you might think that this is how developers see their own paradigms. You would expect that the developers, they are using a component-based approach. They see their approach, they'll say, hey, this is great. I can assemble my components in a great way, making something great. But the mono-repo developer, they have no idea. They have just a pile of garbage. And the opposite way. So the mono-repo developers, they would see the component-based paradigm as something very old, probably inconvenient or incomplete and difficult to manage. But we are developers. That means that we always see the grass is greener on the other side. So typically, developers using the component-based approach will always complain about their approach, and they will think then the grass is greener on the other side, and a mono-repo will solve all their issues. And the other way around, typically, I've heard a lot of mono-repo projects, and the developers, they were complaining, saying, no, should really move to a component-based approach because it's going to be so much better than the mono-repo thing that we have now. In reality, it happens that many times we cannot even choose. Because of Conway's law, we are constrained about our organization, right? And if we are developing a large project, it's very likely that our organization will have constraints. There will have different teams. It will have business constraints. We have to deliver our products to different customers in different ways, right? And all of that defines how we can develop software, right? There are a couple of corollaries and examples there. For example, you can see the organization chart of a car company in the dashboard, and also see if the steering team hates the heuristic team, right? So you can see everything from an organization in the product, in the architecture of the product itself, especially in software products. So we are not even that free to choose, and we have to adapt our organization and the way we develop software. So when we are talking about these two development paradigms, the mono-repo one is basically we have a large project. It can be a single repo project, or it might have some tooling, like it might have submodels for the subprojects. But the core idea in the mono-repo is that we have a monolithic build. You basically change something and you build the whole thing in some way. While in the multi-repo approach, we have one different repo for every different component. They are in the dependency graph, and they are kind of connected to each other in some way, right? When you're building something in a component-based approach, you don't have to build the whole thing. You can perfectly go to one of these repos, check it out, develop, and do some changes, and build it seamlessly. And you don't necessarily need to propagate all those changes to the whole project. There are also like some organizations that are using some kind of hybrid approach. This is also typical, like the organization managing their whole product like in a mono-repo, and then they can have the third-party dependencies as external components. For the sake of this talk, this is really not relevant, so I'm going to stick to the mono-repo and multi-repo approaches. In the mono-repo approach, we have this monolithic build that typically implements the leaf at head paradigm defined by Titus Winters in Google. Regarding tooling, it's very common to see different build systems as Bazel and Back used for mono-repo, monolithic builds. But it is true that I have also seen very large Visual Studio solutions with hundreds, many hundreds of sub-projects there. I also consider that like a monolithic build. So Visual Studio is also used for mono-repo solutions. For example, in video games, this is already the use approach. These tools use a very, very heavy use of compilation cache, like Ccache, Hcache, anything, because you are basically building everything all the time. So you either use compilation cache or your CI, your build is going to take forever. And as a result, they typically also need very dedicated and optimized build infra. Sometimes the repos become so large themselves that they might use a special tooling for the Git checkout. The advantages of the mono-repo approach is basically that you don't need to version. You live at head. I mean, you don't care at all about the changes that you do. You don't need to give them a number, right? You just move everything at head. But of course, the disadvantage is that there is no versioning. So that means that if you have to deliver your software, for example, to different customers, and you have to support them back in time, give them patches and everything, living at head, which means you only have one version, which is the latest, is bad. The life at head works better for an organization like Google, that everything's on the server side. But as you have to deliver your actual products to your customers' machines, then it's more likely that you might need some versioning. On the other hand, the multi-repo approach implements the classic versioning paradigm, in which you can take one of those components, you can do some changes, and you can do an independent release. You can do an independent build and release of one of those components. The tools used for multi-repo are the typical suspects like CMake, Makefiles, MSBuild, Mesons. Caching, of course, using Ccache or Hcache is also useful. It's always useful if you want to. But also, cache happens typically at the package management level. You typically cache your dependencies, binaries, so you don't have to rebuild your dependencies all of the time. The advantage is that you can do that. You can just check out one of the components, work in isolation, work on that specific component, build it, and create a release, a new version of it. But the disadvantage is that you have to do a per component version and release. And that's the major problem, that's the major challenge that I wanted to focus. Today, we are going to focus on this problem. We are going to alleviate this problem, especially for larger scale projects. Let's define first the problem. So the things that when we have a dependency graph and we are working in a multi-repo approach, in a component-based approach, we have this dependency graph of repos. They are connected in some way, right? So building it is relatively fine, but the problems start when one of these components starts to get changed, right? Someone gets to this specific repo, edit the files, they are creating a new version, right? And the thing is, okay, someone changed that, but now we kind of need to guarantee or at least check what happens with all the downstream consumers of that specific repo. Even if you create a new version release, it might affect somehow the consumers of this specific repo. And so we need to check that down the dependency graph, hopefully in an efficient way. Today, I'm going to use this project. This is a real project. I have this in GitHub, right? Every one of these boxes is a different GitHub repo under my username. I'm going to use these 4 static libraries, and then I'm going to define 2 executables applications. It's simulating like a small video game in which we have the game itself, and we also have a utility, an application that's a map viewer, right? The idea is that our final products are the applications, is the actual thing that we need to deliver to our users, our customers. So when we are working in a multi-repo approach, the idea is that every developer, they can, at any time, they can check out one of these components, for example, Mathlib. And they do a clone, they move to the folder, they prepare their build. In general, we can do Conan install in this case to fetch the dependencies, if there are any dependencies. In this case, there are no dependencies. it might not be necessary, right? But it's just a generic thing you typically install, you configure your project, and as part of the configuration of the project, you might want to install the dependencies. And then you use your build system, CMake, for example, create your project, open your IDE, and work on that project. That's the typical development flow for a component-based approach in multi-repo. When when that developer is going to work on some of the components down the graph, for example, the AI component, right? They will do the same. They will do a clone of the AI repo, move to it. Conan install, in this case, it is necessary, right? Because the AI package has dependencies. It's depending on Mathlib, right? So if the developer wants to work on AI, they need the dependencies there, right? So that will be like a preparation step before we can actually start coding on the AI code, right? So the idea that the Conan install in this case will fetch the dependencies, Mathlib in this case, download it from the server, put it in your machine, and then you're ready to start using CMake, for example, create your project, open your IDE, and start working on the AI code. So the basics that we need to know about package management and dependency management, in this case for Conan, is these three operations. First, when a developer wants to start working on a component in a multi-component paradigm, right, they need to install the dependencies. In this case, Conan install. It will be downloading the dependencies, putting them in your computer, and making them available for you to work. Right? Once the developer has finished doing the changes, right, they need to create a new version, a new release of the packages that contains the change they did. Right? That will be a package creation that's a Conan create, right? And finally, if the developer wants to make those packages available to their colleagues or to the CI jobs for them to work, that will be a Conan upload to get the packages from your machine, put them in the server, and make them available. Of course, when we are talking about packages actually can contain multiple binaries. Let's say that we are developing here a game and we want to support the Linux system, right? Our packages in this dependency graph, they will contain two binaries. One binary for Windows and the other binary for Linux, right? So when we are talking about this package thing, we are actually talking about two different binaries for the different platforms that we are supporting. This could be any number of binaries, right? I'm going to use all the examples and the demo and the code here for two configurations, but the idea is to scale to any number of binaries that you want. If you want to support like consoles, the PlayStation and the Nintendo and whatever, you will have basically a different binary there for every one of your packages. So when a developer is working on one of the components of the dependency graph, they will do the clone, they will do the Conan install, and typically the dependency manager should manage this. Hey, you are a Windows developer, you are developing in a Windows box, right? I only need to install for you the Windows dependency, the Windows binary for your dependency for Mathlib, right? So that's enough for the developer to start working on the AI package, right, on a Windows machine. So far, so good. No problem, no integration, no continuous integration problem so far. So the problem starts if the developer, they did a change to the AI, right? They changed the source code, the headers, right? So they decide to create a new version. That will be the AI 1.1 version, right? And then they create a package for that version, right? And then they upload the package to the server. That's where the problem starts. Two things can happen, right? If our dependency graph pin versions do requirements, in this case, for example, the engine package requires that it has a pin version to AI, then that's perfectly fine. Why? Because a developer, my colleague, can be cloning the game, installing, and they can perfectly work in game because my recently created AI 1.1 package will not be affecting them at all. It's impossible that that package can break them, right? Which means that this is not a continuous integration scenario. Why? Because yeah, I created a new package, but this change is not integrated down the dependency graph into my products, which is the continuous integration. Continuous integration in this area means, hey, I want the changes that I'm doing in the AI, in this case, I want to integrate them into our products to deliver the value of my game to the users as fast as possible, right? That's the goal. So this is not a CI scenario, but this is, right? It's very typical when you're using dependency management that your actual requires be something like this, using a version range, right? Our engine package could contain a definition with our requires to AI in this specific range. That means that if my colleague developer, they start working on game and they do a Conan install to be able to start touching the game code, their dependency graph will automatically resolve to this and will include the AI 1.1 in the dependency graph. And this is where things can start to get messy. So this is the formal definition of the problem that we are trying to address today. We have an hopefully API compatible change, right? And what we want to do is integrate this change in our products. That means build and test the necessary packages down the dependency graph, down to my organization products, right? Because the products is what I really care for. This is what I need to deliver. And I want to do this in an efficient way. That means do not build more than necessary. In this example, it's very clear. I'm 100% sure that I don't need to build Mathlib, graphics, or MapViewer at all. So if I have an approach that, hey, just rebuild everything from source, I'm wasting my resources, clearly. I wanted to do it fast. For example, I want to parallelize. Let's say that the developer did changes to Mathlib. I know because of the dependency graph that I can build AI and graphics in parallel because they are not directly connected to each other. Right? So this is a parallelism that my CI can exploit and can use to be faster. And finally, I want to do it safely. I don't want this process of integrating things to break my other colleagues' jobs or the other CI jobs. Let's start with some basic pieces that we will use in our approach. First, we don't want to break the build. That's important. We don't want to affect or disrupt our developers. But we are causing some disruption because we uploaded a package there that package will become part of the dependency graph, and we have no idea so far if it can break them. It can break the engine, it can break the game packages, right? So what we did here is not great. So the first principle here is using the multi-repository approach, right? This is a DevOps principle that in this case JFrog has done for many years for many different technologies, right? And it works really well. It means when the developer is doing the changes and they are creating AI 1.1, you don't want to upload that package to the repo, the server repo that everyone is using, right? Because if you do that, you might break them, right? So the idea is that instead of doing that, okay, I'm going to put this package. It's there, I built it, it's looking good, but just in case, I'm going to put it in another repository. I call it the packages repository. I have these two repositories. Develop is the one that every developer is using, right? And even CI jobs are using. And the packages repo is a separate repo, right? When I'm going to put the packages that are still not validated, right? Let's say that this is the equivalent to having branches in source control, right? What do you do when you have some changes in source and you don't want to affect your developers? What do? Put it in a branch, right? You put it in a branch and you can upload the branch to the server so your developers are not affected. They can check those changes if they want, right? In the same way, a developer can perfectly opt into using your packages repository, but not by default. So uploading some packages to a different repository is the equivalent in source control of branching and putting those changes in that specific branch. And then there is another important concept, is the concept of package promotions. When we have validated, let's say, partially our AI 1.1 package, in the packages repo, we can run a promotion. A promotion is a copy. I'm going to take that thing and copy into a different server repository, in this case, the products repository. And this is basically the equivalent of a merge. When you are merging some branches, you're basically taking some changes, integrating another branch to make them available for other developers or for other jobs, right? A promotion in the server packages realm is basically that. When you are copying one thing from the packages repo that is maybe kind of private to you, and you're copying it to a different repo, like the products one, you are making it available for someone else. In this case, a different CI job, which is basically the equivalent of doing a merge, right? And a very typical question is, but why can't I use just one single repository on the server side and then change the name of the package? Right? There is a principle there also is a general DevOps principle that is packages should be immutable. Once you build something, it should be immutable. It shouldn't change. It shouldn't change the identity of that thing, the name of that thing, right? Because changing that is problematic. The equivalent of this would be, if you're in source control, you have one branch, and then the changes that you want to push, you want to create a new folder with different name under that branch. And then all the changes apply. That's the equivalent of having packages with different names in the same repo. You don't want to do that. You want to have different branches with exactly the same file system structure, the same file system names, right? And finally, the last principle that we will use today is the packages and products pipeline. The package pipeline is the classic one. When we are doing changes in AI, right, typically is what building AI means. There are some changes, you run the unit test, you build the thing, you check that it works, and that's fine. Right? That's the typical CI flow for a package. And then the most important one is the products pipeline. The products pipeline mean, let's build my actual business applications. In this case, game and map view, right? Because this is what you want. This is what you want to deliver. The important thing here is that these products can also have like multiple versions. It's perfectly valid to have an approach in which you have game 1.0 and also game 2.0 in your products. Why? Because you are delivering game 1.0 to some customers and you are delivering game 2.0 to other customers. And the whole approach that we are explaining today works perfectly having multiple different versions of the same thing defined as products. I'm going to just use these two ones, but keep in mind that this scales to different versions of the same package as well. Good, let's check the project setup. I'm going now to switch to actual code. This is what I have. I have an Artifactory instance with 3 repos there, right? And in the develop, 2 of them will be empty. That's my initial state. And then the develop repo will have the packages. So let's have a look. This is my my Artifactory running here. So I can see that I have 2 empty. The packages repo is empty. Sorry, this is not working great. Hold on. Okay, yeah. So these products and packages repos are empty, right? While the develop repo contains the binaries with them for all the different packages. For example, we see 2 different packages. One will be the Windows binary, and the other one will be the Linux binary. Okay, so we have the initial setup that corresponds to basically this. And I can show you, for example, if a developer, well, first, I have also a checkout of all the different repos that compose this project, right? I'm going to change to one of them, and let's say a developer, they just want to install the game, requires game 1.0. I'm going to use a deployer just to make a copy for convenience. Okay, this will go to the server, right? Download the thing and runtime deploy. And I can hopefully run my game, which is basically the code is doing nothing. It's just prints for the different things. So I can see the mathlib running here. I can see the AI with a message that we will change later. We can see also some messages related to the AI, then the graphics, then the engine, and then the game. right? So that's my game running. Everything is looking good. So that's my initial state of the project. Okay, so then the thing will start with a change, right? A developer will come, will check out the AI repo and do some changes. The changes that will be proposed, I'm going to summarize here. I will do these changes later on code, and I will do the full demo, right? So I'm going to change some messages in the CPP file, right? Like some small improvement, bug fix, right? I'm also going to change a default parameter in the header, in the public header of the package, just changing the default intelligence level of the AI to 50. And as I did some changes to the public headers, I'm going to bump the package version. Hey, I did some changes. That's a new thing. I'm going to bump from 1.0 to 1.1. These will be the changes that I want to process in my CI. So the developer, they will test it locally, will be happy about the changes, and will say, okay, that's it. I'm going to commit, I'm going to push to the server, and then the CI will take it from there. So this is what the package pipeline will do, right? I'm going to use GitHub Actions in this case, but it can be implemented with any system. The push event will trigger the main agent, and the main agent will fire two build agents, one for Windows and the other for Linux. These two agents can run in parallel the two configurations for Windows and Linux for the AI changes, can run in parallel, and they can upload the binaries that are going to be built, they can upload to the packages repo, right? Then if both agents finish successfully, it means everything is looking good. This means the code changes are valid, not breaking anything at the package level, not breaking anything at the package level only, right? It can gather the information of the things that have been built and then decide, okay, I'm done here. This CI pipeline, this CI package pipeline is good. I'm going to put the products, I'm going to put them as products for the next stage of the pipeline, which means a promotion. It will be copying the binaries that it built in the two build agents. It will copy both of them at once to the product repo. Why this flow here? Because let's say that one of them passes, the Windows one passes, and the Linux one fails. If you don't do that, and if you make the Windows binary available, right, then everyone else, the Windows developers in your team, they will be happy, right? But then the Linux developers, they will complain to you, hey, you did something and it's breaking my build. Probably not for the Windows developer. So basically, you want to wait until you are sure that both Windows and Linux build correctly. And only when both of them are built correctly, then you promote them to the product repo to make them available. But that's a key concept. You don't do that until you validate that the changes are working in all platforms. Right? And that's the quality stage. Okay, so let's say that for any miracle, the Windows agent starts faster, right? And it starts doing the build, right? Which means in the build agent, it will be cloning the code, it will be calling the Conan create to create the package for AI, right, for the Windows profile, which means that the dependency management will bring mathlib 1.0 into the build, right? In some way, the mathlib 1.0, right, will be part of the binary that I'm building for AI 1.1, right? And then when in the last step, the binary is uploaded to the server, to the packages repo, right? The binary that I created has some binary information there using mathlib 1.0, right? The build is distributed, right? I triggered a Windows agent, and I also trigger a Linux agent. Let's say that the Linux agent takes a bit more time to provision for some reason, right? And then the thing starts here. But in the meantime, there are other teams. We are talking about large scale CI, which means there are other teams that are working, for example, in mathlib, right? And the team that is working on MATLAB, they decided to create a new version. For example, MATLAB 1.1, right? And their MATLAB 1.1 passed all the process, all the validation gates. Everything was looking great for the MATLAB team. And then decided to put the MATLAB 1.1 version there for everyone else in the company. Hey, it's ready for production, right? And it may be ready, but if my ongoing job starts building now, it's create a package for Linux for AI 1.1, it will use the new MATLAB 1.1 version, right? It will work. It was validated by the MATLAB team, so it's not going to break it. But this is what I built. And then when the build uploads the binary to the server, even if we managed to build both binaries successfully, it happened that we built against different versions of the dependencies, right? Because my build was distributed, something changed in between those two jobs, right? And now we have something that can be pretty annoying. It can be difficult to understand. It can be difficult to debug if something goes wrong. We are going to waste hours because we didn't build against the same set of versions of the dependencies. So this is not what we want. But what we want is, okay, when we are starting this job, we are going to take a snapshot. We're basically a picture of the current state. So let's take a picture of the develop repo. Like that's called a log file. That's one of the uses of a log file. Log files have different uses. One of the uses of a log file is take this snapshot, right? In this case, the snapshot is repeated for the different configurations, Windows and Linux, and it generates a file that basically pins the version and the revision. That means, hey, log file contains MATLAB 1.0 because that's the current state of the develop repo at that specific point in time. Then, if we do this before triggering the build agents, right, and we feed this Conan log file to the build agents, then we can guarantee that the dependencies, the set of dependencies used will have exactly the same versions. When the Windows agent triggers, yeah, that's fine. There is only MATLAB there. My binary is using MATLAB 1.0 only. And when I upload the binary, of course, it will be MATLAB 1.0. And then when, yeah, by the way, it will also create this process here. When you upload those packages, you can also create a manifest of the things that have been uploaded to the server. I will explain later why this is useful, right? So then, when the Linux agent starts, right, even if someone else introduces a new package there in the server, just because we have the log file there, it means that the Conan create will pull the dependencies. It will enforce to use exactly the MATLAB 1.0, exactly the same version and revision that the other job was using, right? So when the Conan create finishes and the Conan upload happens, it will upload to the server a Linux binary, in this case, that has exactly the same set of dependencies that the Windows build as well. And this is exactly what we want. We want to have this consistency across our dependencies. And finally, it will also create a manifest of this file.
Previous slide when you created the log file.
This one?
Well, phrase and then PL two things, but generate a singular log file that you can build.
Exactly.
You know when people see it.
That's correct. So the question is, here I was running to log create operations, and the question is if it creates a single file. And the answer is yes. The Conan log create is cumulative also, as long the first line here, the first Conan log create, will already create a Conan log with some contents, right? The second Conan log create for Linux will find the existing log file and will extend it, will augment it. This is important. In this case, it's trivial, right? My dependencies are always the same in Windows and Linux. But what happens when there are conditional dependencies? If your dependencies are not exactly the same in Windows and Linux, and that happens, there are recipes there that say, hey, if I'm in Linux, I require FMT. And if I'm not in Linux, I'm in Windows, then I will use STD format for some reason, right? And this happens all the time. That means that your dependencies might not be exactly the same, but you want to create the union, a Conan log that contains everything. For Windows, for Linux, you want to log everything for all configurations. And then the consecutive Conan log create commands for the different configurations does that. It starts with a log file. The first log file actually already pins mathlib 1.0, right? So even if at this point here, the developer repo gets a new mathlib 1.1, still the final result will log to mathlib 1.0. So this is also pretty robust against changes that happen in the middle of the Conan log create process. Okay, so we were here. That's what we wanted. And we also created like the package manifest for the Linux job. So we are here, we are now happy. We created the AI 1.1 package with the 2 binaries that have matching dependencies versions, right? Now we want to collect the information of everything that has been built. In this case, it's relatively simple, but we could have, instead of 2, we can have multiple build agents that are building the thing for those multiple consoles and these multiple architectures that we want to build. So we want a generic way to aggregate the information of all the binaries that have been created. And that's basically a package list merge. The result of the previous step is what is called a package list. A package A is the list of packages that were uploaded to the server, right? That means that the Conan package list merge is basically that. It takes different files. Every file is a manifest of the packages that have been uploaded to the server, and it merges them in one single package list file, which is a manifest of all the packages and all the different configurations, all the different binaries that have been built for, in this case, for AI 1.1, the Windows and the Linux. But this, if you are building 10 different platforms, you will have 10 different files and on the left side, and then you will have one single file on the right side that has 10 different entries with one entry for every different binary that was built in the process. And with this file, with this aggregated manifest package list of the things that have been uploaded, I can finish my package pipeline. Say, hey, this build is looking good for all platforms. I'm going to make available all these binaries to the next stage, right, in the products repo. Just a promotion, which is basically a copy from the packages repo to the products repo. Okay, and now let's try the demo here. I'm going to move to the Conan CI AI, and I'm going to do the changes that I told you earlier. First, I'm going to change the CPP file. Let's change the message here, improved. I'm also going to change the default intelligence level to 50. And finally, I'm going to bump the version to 1.1. Let's save the changes. Let's say that I tested locally, everything is looking good. So I'm just going to push directly the changes. And then I'm going to push to my GitHub repo. And hopefully GitHub is gentle today. And this is the, yeah, and we see that our build triggered, right? And we can see here the structure of the pipeline that I was showing you in the slides. We have first a log file creation stage. I will show you the code now. Then we have the actual build for Linux and Windows for the AI package. And as a final step, we will have the promotion, right? Let's have a quick look to the actual GitHub Actions code. I'm going to close this one. Okay, this is the main job. First, the log part, create the log files. All of this is basically installing Conan itself and configuration, defining the remotes that I'm going to use, right? So the important part here is the log creation step. This is exactly what we were seeing in the slides, and that's the question. Here, actually, I wanted, in the slides, it was a slide where, right? So I removed the arguments. Here, I made the arguments explicit. So it's more clear that the log file out from the first step is fed into the next step, into the one with the Linux profile, right? And that's create a single Conan.log file. Then by GitHub action, we'll be putting that log file in an artifact, in a GitHub action artifact, right? So if everything is good, hopefully I should see here, let's refresh. Yeah, here we have the artifact, our Conan log that was created in this stage. Then, okay, so once the log file has been created and put there, the two agents are triggered. So this is boilerplate, just passing the secrets. And then the Linux and Windows agents are launched as workflows, right? We can see the code here, right? This is all boilerplate as well. This is installing Conan and configuring Conan. This is where the action starts. It first starts by downloading the Conan.log artifact from the GitHub Actions artifacts. And then it's calling Conan create. It's creating the package for the specific configuration. And we can also see that we are providing here the log file to guarantee that it's using the log dependency that we want. So basically creating the package there. If this stage succeeds, then we gather the information. We do a Conan list to gather the information of the packages that have been built in the previous step, and we upload those packages to the packages repo. Exactly what we saw on the slides. As simple as that, no magic here. And our job finishes by uploading the manifest, the package list manifest of the binaries that were built in this very specific job. So when the agents finish, the main pipeline will run the promotion. The promotion, this is again installing and configuring Conan. The promotion itself is as simple as this, just collecting the manifest of every job that has built a binary. It will be merging all these artifacts, all these package lists in a single one, and then it will be running the promotion. Just from the packages repo to the products repo, copy the thing. So if things work, sorry, not this one. Yeah, we can see here that the promotion succeeded. So if we now go to our repos and we refresh, we should be able to see that the product repo got the 1.1 package and it got these two different binaries here for Windows and Linux. This is exactly what we wanted, right? So we managed to build our AI 1.1 for Windows and Linux in a guaranteeing that the set of dependencies are exactly the same without disrupting the developers. If the developer go to the console and say, hey, Conan install game, they are still getting exactly the same thing because they will not resolve. They only resolve against the develop repo. But I haven't put still the binaries, these binaries for AI.1, they are still not available in the develop repo. So I'm not disrupting anyone in the organization. Okay, so now let's move to the challenging part, the products pipeline. And this is what we have, right? Now let's say that a developer enables the product repo. They opt in, they activate the product repo explicitly, and they do a Conan install of game. We know that because we have version ranges, it will resolve to this dependency graph, and AI 1.1 will be there. Right? But this also means this, right? Conan will tell them, hey, you don't have binaries for engine and game. Why? Because it knows it. It knows that there is a version change in the dependency graph, and that means something. Let me explain a little bit quickly the binary model. This is how Conan models the binaries. As a single package can have multiple binaries. Let's say that game could have 6 different binaries for different platforms. Every different binary is represented by a package ID. A package ID is the hash of the configuration. If we have, for example, the build for Windows is represented by that file, right? If we have that file, it will give us a checksum. That's the package ID representation of that specific binary. If we change it and we use still other settings, for example, Linux and GCC, a different compiler, right? If we have this other file, we have a different result because we have a different package ID. right? So that's kind of the simplified model. If we change anything in the architecture or a static or a shared library, anything that changes our binary will produce a different configuration file, which results in a different package ID represented that binary. Right? What is important for us today is this. The version of the dependencies also affect the binaries. They affect the ABI. Right? In this case, building against AI 1.1 and AI 1.0 is not the same. We will have two different binaries of game if we use a different version of the dependency, right? That's it. So basically, the way to represent that is you need to factor in your dependencies identifier, dependencies versions, and probably even more, right, into the package IDs of the consumers using those dependencies. This is a bit more advanced. I'm going to go through this quickly, right? In practice, not all dependencies are the same. If you are building, for example, an executable against a static library, no matter what changes in your static library, the binary code of that static library is going to be embedded into the executable, which means typically, no matter what the changes you are doing to the static library, you want to rebuild the executable, most of the cases. Right? While if you are in the so-called non-embed mode, if you have an executable linked to a shared library, and you only change the CPP files of the shared library, the implementation details of the shared library, is guaranteed that you don't need to rebuild the executable. The interface doesn't change, right? And then you're good to go. Which in practice means that Conan can leverage that, say, hey, let's say that a developer, they are only doing changes to the CPP files. Okay, that's fine. That's an implementation detail, and I know this is a library, so I can bump only the patch version of that library. Which means, hey, consumers, if you are not embedding my current binary, you don't need to rebuild yourself. You are good to go, because I'm telling you that my changes are not ABI changing, and you don't need to rebuild. But if I'm doing some changes to my public headers, like the one that I did for the AI, I changed the intelligence default parameter, that might affect your consumers, right? That was API compatible, but that might have an effect on the API of the consumers. In this case, I'm going to bump the minor version, which means, hey, you might need to rebuild. You need to rebuild against me because I changed something in my public headers. I promise that I won't break you, right? But you need to rebuild because I'm going to affect your API. And finally, if you are changing your public headers in an API breaking change, then in an API incompatible way, basically you want to bump the major, which is automatically excluded by the version ranges. Version ranges will typically exclude the next major. That's the typical behavior. So in any case, the important thing here is that Conan knows that because we have a new version there, we need to rebuild engine and we need to rebuild game in that specific order, right? That's necessary. So Conan has the facilities. So it can add a data build missing, which means, okay, I know those binaries are missing, I will build them for you, right? In that order. So if you add the data build missing to the command, it will no longer fail, and it will trigger first, it will trigger the build of engine, and it will trigger the build of game. And this solution might be a perfect continuous integration solution, right? For some cases. Basically the case when you have one product, one single configuration, and a centralized build, right? You can afford to build the whole dependency graph. Let's say that this graph is 300 packages of that dependency graph, and you can build all of that if necessary in a single machine, right? If you can do that, then this might be a good solution. But for a scale and for managing multiple products and multiple different platforms, this is typically not enough. What we know is that we should be basically implementing this. So this is kind of the solution that I'm going to expose. Then I will explain how to implement this solution. So basically the idea is when we want to integrate the products, right? We want to build down to the game a map viewer, right? The first thing we will do is, of course, we will capture the log file. We will know that we want to take this snapshot to guarantee that the set of dependencies are consistent for all configurations, right? Then we know, because we are humans and we are smart, we saw the dependency graph, we know that we need to build the engine, right? The first thing. And we want to build the engine for both Windows and Linux, Right? So this will be like what's called the level 0 of my CI. Right? When both agents have successfully finished, we know that we can move to the next. Of course, we can upload those binaries now to the engine repo, to the products repo, the binaries for the engine, right, that were built. Right? And when this happens, we know that we can move to the next stage. Right? We can now start building game against both the binaries for engine, the new binaries for engine, and the binaries for AI.1.1. Right? And we can create the build agent and the Linux agent for game. And when it's finished, we can upload those binaries to the products repo as well. Right? Finally, if everything went well, it means the AI one-to-one changes integrate cleanly into my products. Right? At this stage, I can say, okay, I'm ready, this is working. I can collect the information of all my dependencies, the things that I build, and I can finish my pipeline by making this available to all the developers. Right? Basically promoting these packages to the developer repo. The moment we do that, we are making available AI 1.1 to all developers in my organization and CI jobs. But they are fine because we already tested that the AI 1.1 works fine with engine and game. And we also build new binaries. So if a developer is checking out game, they will do a Conan install and they will get the new binaries for engine and AI.1. And everything will work because we have already done it in CI. So the first step is pretty simple. We will just capture the log files. In this case, we need to capture the log file not only for every configuration of game, but we are smart humans. We knew that the map view is not affected, but an intelligent CI system doesn't know that, right? So the idea is, okay, just let's collect a snapshot, a log file of all the configurations and all the products, one at a time. Right? So basically iterates game for Windows and Linux and then map view for Windows and Linux. And it will result in this snapshot, this log file that captures the dependencies, including, in this case, the AI 1.1, because it was already available in the products repo. Right? And this is the chain that we actually want to test and want to integrate. Then, the next step, okay, we already have the log file. We need to trigger the builds with this log file. Right? We will need to trigger this other thing, but here you are abusing something. Diego, you are abusing that you know the graph. This is an example. Right? In practice, how can I implement this? The first thing and the first typical mistake implementing a CI is trying to implement this kind of knowledge about the dependency graph in the CI system. That's a huge maintenance pain. You don't want to do that, right? So what's the solution here? We have a dependency manager. We can query the dependency manager and ask them, hey, what is what I need to build and in which order? Right? And that's a command that we have. It's called the Conan graph build order. The Conan graph build order, if you type that command and, hey, create a JSON file for me, it will be basically outputting this, which is, it has first a list there which contains engine. It means you should be building engine first, right? And you need to build engine, this specific binary, this specific package ID, you need to build it. And these are the arguments that you need to build it. Right? So it's basically all the information you need to trigger a build of engine, right? And then the second list there is containing game. So it knows that first it has to build the first list with engine, and then it has to build the game. The game depends on engine, of course, and it also has the information there about the binary it needs to build, right? This is basically the information that we need for a CI job to automatically launch what it needs to build. So this can be leveraged by the CI. In practice, we have a number of configurations and we have a number of products. So what we want to compute here is not just the build order for game for a specific configuration. We have two different configurations. They might have different dependencies. There might be some existing binaries for some of them already. Right? So the thing is we can iterate and we can build for game, we can request the build order for game for Windows. And it will create a file for us. And we can also request for game the build order for Linux. And this will give us two different files. Right? Then we can repeat the operation for the map view. Right? We will request what is the build order necessary for map view for Windows, and what is the necessary build order for map view in Linux. And it will also create two files for us. Someone can guess what it will be the content of these files here? Empty. Of course, we know it very easily from the graph because we know that map view is not affected. These files will be empty, but that's perfectly fine. The system can handle this perfectly. It's perfectly good. Okay, what do I need to build in map view because AI got some changes? Nothing. Done. So basically, these 4 different files or n different files, we can aggregate them with a graph build order merge, which means, hey, take all the things that I need to build, aggregate them into a single file. While this is another very common mistake in CI. If you try to parallelize, simple parallelization of game and map view in parallel, right? And they have some common dependency that needs to be built. You are going to build that common dependency twice. You get one for each job, right? But if you compute what needs to be built and then you merge it, that dependency that happens in the two dependency graph of game and map view, it will be a single thing in the merge build order.json. And then when you use that build order.json that looks like this, then you won't repeat building the same thing twice, just because it belongs to different products. For map view and game is very simple as well. Consider again the case of having game 1.0 and game 2.0. Then the common state of dependencies are larger, are typically larger, right? And you don't want to waste your resources rebuilding things. So the resulting build order merge is something like this. It will also be a list of lists. In the first level, we see engine. And now in engine, we see that we have to build 2 different packages IDs. We have to build these 2 different binaries for Windows and Linux. And then in the second level, we have game. Again, we need to build 2 different binaries for the game. Right? And if we want to correlate, also, we have a file names there, and we can actually trace back to the arguments, to the profile arguments that you need to feed into the system. Right? This means that this information in JSON can be automatically used by a system to do this. This is basically the unroll of that JSON in commands that you want to repeat for every level. The first level, 0, right, is for building engine for both Windows and Linux, which is basically a build engine, create a package list of the things that have been built, and then upload the thing to the server. And then you do that for Windows and for Linux. When you are done in level 0, then you move to level 1. And then you start with game, repeat, build both for Windows and Linux. And at every build, you capture a manifest of the things that have been uploaded as well, which in this case, it means 4 files. Right? In practice, you are not unrolling the thing. In practice, in GitHub Actions, I will have to unroll the thing. But in reality, what you want to implement is this. And you can do this in Jenkins. It basically does the nested for loop that you need to implement the CIR scale. Right? It's basically for every level in your dependency graph, the topological sort of your dependency graph. For that level, you can build those packages in parallel because they are not interconnected. Right? And inside of every package, you can build in parallel all the configurations for that specific package as well. Right? Which means install, create the package list, and upload the result to the server. So if everything goes well, the graph build order will automate these 2 boxes here. Right? It will implement these things in a fully generic way. And then we will have the 4 files of the things that we have uploaded. Right? And with these 4 files, we can finally merge them into a single one. Right? Everything went well. I have my final manifest, and I can run the promotion. The final promotion of everything that has been built in this products pipeline will be copied to the develop repo.
Is that about?
Yes. So the question here is if this promote command is atomic now. And yes, this very specific one is atomic. Basically, it works. This is an Artifactory command, but it's using the Artifactory API, which means if you have the packages in the products repo, right, you run an API command that say, hey, copy them from the product repo to the developer repo. That's basically a no-op because Artifactory implements file deduplication, which means the actual artifacts are not copied at all, right? It's just an entry in the database. So it's basically taking the references of those things, AI 1.1 and the different binaries that were built, and making them entries in the developer repo. And that is, in theory, a promotion is atomic. So they will be created all at once. And this is basically what, I know the pain. This is what you want to. This is exactly the same. When we were creating the packages, the Windows package first, in the package repo, then we created the Linux package later and put it in the package repo, and we ran the promotion, was exactly the same. We want to do it that atomically, because if you do that atomically, then the Windows agent might get access to the Windows binary first, and then the Linux agent might fail because the binary is still not there. So my GitHub Actions are not using, I didn't have the time, my fault, but it will be, are not using the atomic one. They are using like a poor man download and upload, which is not atomic, but the art promote is already atomic. So it will be fine. So, and then that's finally the promotion. And now let's cross the fingers and let's see the demo. Okay, so here I have the products pipeline. I will show you the code. Basically, let me close here. What I call the products repo is basically an empty repo. It doesn't contain any code at all. It only contains the actions to build the products, right? So these are the workflows that we will see later. But what I'm going to do now is I'm going to the actions. I'm going to first show you a whole build of my application, right? So I triggered this before to build everything at once. So we can see here that we have the different stages, the computing, the build order, the log files, and the build order actually. Here, we can see in the level 0, we have 2 different builds for Windows and Linux, right? For Mathlib. This is the Mathlib build here. In the next level, we have 4 jobs, right? It's building AI and graphics in parallel, right? So these 4 jobs here are parallel builds because AI and graphics, they don't depend on each other. So they can be built in parallel for both Windows and Linux. Likewise, in the next level, which is level 2, right? I can build both engine and map viewer concurrently because they are also not connected to each other, right? So I can build all these things in parallel as well. And the final job is building the game itself. Level 3 is building the game for the 2 different configurations, and the final step is the promotion, right? So I'm just going to trigger the job here, rerun it, and let's see what happens. Let's see if it starts, and I will be explaining the actions while this works, right? So now is computing the build order. So let's have a look at the CI actions here. Okay, so this is the computation of the build order, the initial job here. All of this is just installing Conan, configuring the remotes. We now see the first step, the log create. It's as simple as this. In Jenkins, for example, you can do just a for loop, right? It's easier to do that, to iterate your products. But in this case, I'm capturing the log file for game, Windows and Linux, and then for map viewer, Windows and Linux in a cumulative way. So the result of this will be, again, one single log file that represents all my products and all my configurations. I will upload this log file to the GitHub Actions artifacts to make it available for all the other jobs. And then I will compute the build order. And this is exactly what we saw. Just iterate for every product and every configuration. I will create a build order JSON file of the thing that needs to be built. The final step is let's take all the graph build orders and merge them into a single file. And this single file now is the kind of the trick that I need to implement with GitHub Actions. I'm going to define an output. That's a GitHub Action output, right? This is the way that I'm putting the build order here, right? And I'm putting in a GitHub Action because I can use this GitHub Action as a parameter for matrices in the next levels. So the main challenge that I face, I wanted to do it in GitHub Actions, is that GitHub says you cannot do a for loop, right, to dynamically create jobs. It's not that easy, right? So what I had to hard code here is different levels, but that's perfectly fine because it's basically copying and pasting them. And if, let's say, you move to 10 levels of nested dependencies, you can have very large dependency graphs. So that probably will not be the limit. I will summarize about this later. So basically, every level contains, if this level is not empty, right, I will run a matrix of the packages that belongs to this level of the build order and the different configuration that I want to build. And I will trigger this builder job here, right? So let's see the code of the builder. This is all boilerplate to pass the secrets. This is taking the inputs. This is basically installing things, configuring things. And this is the actual action. This is first get the log file to guarantee that I'm doing the right thing. And again, this was an inconvenience of GitHub Actions because I couldn't be like programmatically do that. So I had to kind of expand and roll the condition here. But basically, it's the same thing. It's just running Conan install for the specific package that I'm building in this level, providing the log file. Sorry about that. Providing the log file and for the configuration that I want to do. So all these lines here are basically implementing the same. It's just the creation of the package. Here is collecting the things that were built and uploading those packages to the server. And finally, creating the manifest of the things that have been uploaded and uploading them to GitHub Actions artifacts. So let's see how the pipeline goes. So we can see here that it has triggered in the level 0, it has triggered the build of Engine, both Windows and Linux. It hasn't triggered Mathlib or anything, just Engine, because it knows it has to be Engine, and in parallel Windows and Linux, because it knows it can do it in parallel. And in this second level, of course, Linux finished first, is still building Windows, right? Okay, that's great. And we will see in this case that level 2 and level 3 were skipped, nothing to do here. I only needed to build Engine and game, and I'm done. And finally, the job starts the promotion. So what is the promotion? The promotion is in the main workflow. When all the levels finish, one after the other, right? The promotion will be basically the same as we already did in the previous package pipeline. It's basically installing Conan, configuring the remotes, gathering everything that was uploaded, right? And running a promotion, merging all that in a single upload.json file and running a promotion. This is exactly what is not atomic. I didn't use Conan art promote, which is the atomic thing. I'm running here like a poor man download and upload, which is also a promotion. That's basically the concept of a promotion. But it will be slower and it will not be atomic. So I need to change that to make it Conan art promote. So let's see if our build actually finished. Promotion finished, which probably means get status Conan list. I should be able to do the Conan install requires game.10 deployer runtime deploy. We can see now there in the information that the dependency graph is now resolving to AI 1.1. It deploy my game, and if I execute my game, I see that my changes in AI 1.1 are part of my game, and they were cleanly integrated and automatically integrated in this way into my products without disrupting I as a developer. This was transparent to me. I was never broken any time, and I got the changes transparently. Okay, so I skip a few details here, right, about the strategy. The general integration strategy for an organization, it really depends, right? For example, the integration strategy. Let's say that you are triggering the package pipeline for every change in AI, right? And then you might be able, hey, just after you trigger the AI pipeline, you can trigger a full products pipeline for every commit change in AI. But maybe that's wasting too much of your resources, just testing your whole products for every single change there. So organizations might decide different strategies. For example, it's perfectly fine if you get only the package pipeline for AI, and then you accept the pull request, you merge it, you promote the packages there, and then the integration is triggered after the changes have been accepted, like the pull request, reviewed, merged, right? And then the products pipeline is actually triggered after the changes. And of course, it will use less resources because it will not be building every single commit of the developer changes, right? Or if the scale is probably too large, and I've seen this, the actual product integration happens nightly. So all the developers, they are creating new versions all the time, putting them in the products repo, right? But then the products pipeline is only triggered nightly. And it tries to get all the different packages of the different developers and then do a build. If everything goes well, perfect. If not, the developers will be notified the next morning and they will take action to try to make their nightly build green again. Okay, so time to finish some conclusions. In this talk, I've shown that CI at scale with a package-based approach is possible, right? Not only possible, but it's possible to do in an efficient way. We have shown that it's perfectly fine not to rebuild the world again and again just because we have a package-based, a component-based approach, which many people are just throwing CI resources just to rebuilding again everything just to make sure. It's not necessary. You can just build what needs to be built and reuse all the previous compilations, the previous binaries, and be way more efficient. You can do it safely, just building when it's necessary. When the version tells us, hey, you need to rebuild, you build. But if the version tells you don't need to rebuild, then you don't rebuild, right? And this is already built in. And it's also safe in the sense that we are using log files, and it guarantees something. It guarantees that the set of dependencies are consistent. If we have concurrent changes, we have concurrent processes in our CI, we will always have the log files. We saw them in the actions. The log file is the snapshot that is used. Hey, this build is using this set of dependencies. And this is always kind of a guarantee that you are using those set of dependencies. And this is also important for things like the SBOMs. You want to guarantee those dependencies, consistencies as well. It can be performant. We have seen, for example, that when we are building the whole project from the top, both graphics and AI, they are built in parallel because the system knows that those things are in the same topological level of the dependency graph. They don't depend on each other, and the build can be done parallelly. And it cannot be distributed. We can throw the build to different agents in parallel. We can scale horizontally as much as we want in an easy way. We have also introduced some principles that are very well known in the DevOps industry for a long time. But we in the C++ community, also because there were no package manager before, honestly, they have not accepted, they have not adopted yet. Some of them are very important, like package immutability. A very common mistake is a DevOps mistake is you build something, you test that thing, right? And then after, when you're going to release, you rebuild it again. Hey, which means that what you're releasing is not what you tested, because many things can change in that process. So the package immutability means you build it, and everything that you build and you test and you QA and whatever, that's the thing that's going to deliver, right? Also the principle of multi-repository. We have seen the parallelism between source branches and source merges and using multiple server repositories to be able to create different packages without disrupting other developers. And also the way of using package promotions as a way to make those binaries available to other stages and to other developers. And a very important principle, one of the major mistakes in CI is implemented in the CI system itself. Hey, I got here this package, mathlib, right? So when mathlib changes, that triggers a build in engine or in AI or whatever. It's basically implementing the full dependency graph, hard coding the dependency graph in the CI system itself. I've seen this so many times, and it's so painful to maintain that it's probably one of the major reasons that organizations might decide to move to a mono-repo, because it's a pain to maintain that solution, right? That is not necessary if you implement a products approach. If you focus on the things that you want to deliver to the customers, and then you compute the things from the bottom up, you actually compute from your game and your map viewer, you compute the dependency graph, that's perfectly doable. It's not only perfect, it's almost optimal in the sense that you focus on the business delivers. We have also seen an implementation in Conan2, which actually, if you remove all the boilerplate there, right, is very few lines of GitHub actions, very few lines. And I'm not an expert. I'm pretty sure that you can also generalize that. You can put things in actions and other workflows and reuse more than I did, right? So it was a pretty short solution without any extra scripting. I hadn't had to use any extra Python script or whatever to implement this pipeline. And this is key. This is scalable. What I did here, I can now increment my dependency graph, and I have a 300 dependency graph there, right? 300 package dependency graph without changing anything in my CI. The same product pipeline implementation that I did will automatically scale without changing a single line. The only thing that I need to do is to create the GitHub repos and put the GitHub package pipeline for building just the package of this. But the product pipeline, building my whole product, will automatically scale. It will automatically adapt to any change in my dependency graph. If you stop using some dependency, that's fine. You don't have to touch the CI at all, right? And it will scale also to any number of platforms. I mean, if you want to add a new architecture, you just add the profiles. You extend Windows, Linux, and then, I don't know, PlayStation, whatever. You add just a new profile there, and the system automatically scales. And you don't need to model that in the CI. My only thing here is, if you are going to do this in production, for the products pipeline, probably you want something a bit more powerful than GitHub Actions, because the YAML constraint there is too strict, too hard. So probably it's definitely worth it to run Jenkins or something like that to implement the product, because then your products pipeline is the for loop, the nested for loop that I showed you before, and it can be implemented in very few lines in a way more efficient. And to finalize, I wanted to give a quick preview, something that I'm very excited. So we have seen this. It seems that we have a decision. You either go mono-repo or component-based approach. And this is no longer true. So we have been working heavily on this. It's a new concept. It's called the workspaces, which means that you can work in a monolithic repo in the sense that this is a monolithic build. It's a super build of everything together, right? So you get the incremental compilation of all the different packages, but at the same time, every different subfolder, everything subproject is also an independent Conan package, right? So this is the concept of a workspace. It is dynamic. You can add and remove packages to the workspace at any time, right? So it's also kind of scale and adapt to your needs. And the good thing is it's already available. It's in an incubating stage there, which means it's protected by an environment variable to make it. You cannot rely on this in production. We will certainly break it, but it's in the latest release. So if you are interested in this, I encourage you to give it a try. And that's all. Thanks very much. All the sources already available in my GitHub account. I need to do some cleanup. I need to put the art promote and everything. And we will move, when it's ready, we will move to the official Conan docs. They already contain something. There is a CI tutorial already in the official Conan docs, which explains basically the basic concepts that I've used today It doesn't contain the full GitHub Actions integration, and it doesn't contain all the details, but it's pretty good. It's just emulating the CI system with some scripts, but the package promotions, the Conan graph build order, the log files, everything is already in there. So I suggest you to give it a look, and we will add the new contents as soon as possible. And of course, if you have any questions, feel free to reach out to us in our GitHub or any of our channels. So thanks very much for your attention.